In 7.5, this is all about solving. And with solving trigonometric equations, you're using identities, you're using a unit circle, you're following directions. So the issue with solving trig functions is that these functions are periodic, which means the answers repeat over and over and over and over and over again for all time. So you have to really pay attention to the domain. Okay, what does it want your answers to be between? All right, so if you're asked to find all possible solutions for sine and cosine, you would add 2 pi k for your solutions. For tangent, you would add pi k. All right, the reason being is because for sine and cosine, they have a domain of their period is 2 pi. For tangent, its period is just pi. Okay, so let me explain what I mean by that. We're going to solve this equation. Okay, sort of like what we do for a quadratic. Okay, I'm going to subtract the 1. I'm going to divide by 2. And then I'm going to think to myself, okay, what angles on the unit circle produce a y value of -1/2? Well, we've got the unit circle here if you really need to use it. Y values of -1/2 are down here in quadrant 3 and 4. That's going to be 7 pi over 6 and 11 pi over 6. So T could be one of those two answers. But then the directions say, and this is key, all possible exact radian solutions for the following equation. So that means I'm going to rotate around and around and around and around this circle. Okay, I'm literally going around and around and around. So I'm going to hit this -1/2 infinite numbers of times. So we take our two solutions and we add 2 pi k. And we add that number to account for all the coterminal angles that exist around 7 pi over 6. So all the times I land here. So whether I do once, around, 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 or the other direction. And how many times I land at 11 pi over 6, right? So around once, around again, around again. I can even go the other direction. Okay? So all possible radian solutions for sine and cosine, you add 2 pi k. For tangent, you add pi k. All right, find all possible. So I want you to highlight that every time you see that. All possible radian solutions. So 2 pi k or pi k, depending on what the trig function is, approximating to 2 decimal places. And here's our function. Okay, it's cosine, so it's going to be 2 pi k. We're going to add the 1. Here we're going to divide by 5. So 0.36. And you're going to do inverse cosine. And the reason I have to do inverse cosine is because I'm looking for a non-unit circle angle. Okay, so inverse cosine gives me 1.203. All right, so the issue here is this gives me one angle. Okay, I know there are 2 places on the unit circle, not even on the unit circle, 2 places where cosine is positive. Cosine is positive in quadrant 1, quadrant 4. Okay, well, if I think about pi over 2 right here, I don't know that exact value, so I'm going to go ahead and get that. So 1.5 or 1.6. So this 1.203 is a reference angle. That means the distance between the x-axis and that terminal side is 1.203. Well, that also means that 1.203 is the reference angle in quadrant 4. Well, remember to get that reference angle, to get those angles, 2 pi minus your reference angle. All right, so I'm going to do 2 pi minus my reference angle. All right, so I'm going to go in my calculator. 2 pi minus, I'm going to put in my reference angle, actually that's a lie. I'm going to do 1.203. That's a lie. Go back to 03. So 5.080. This is going to give me the angle in quadrant 4. All right, now it does say all possible solutions. Okay, so we need to add 2 pi k to each of these. So I have final solutions, 1.203 plus 2 pi k and 5.080 plus 2 pi k. I only need to worry about this 2 pi k or pi k if it's tangent, if it asks for all possible radian solutions. Next example, solve an exact radians on the interval 0 to 2 pi. So now it's limiting my answers. I want only the solutions between 0 and 2 pi. That's just one rotation around the unit circle. Great. I'm going to solve this like a regular equation. Divide by root 3. Okay, I don't know cosecant. I do know it's reciprocal, sine. So if I take the reciprocal of cosecant, which is sine, then I need the reciprocal of -2 over root 3, which is negative root 3 over 2. So I'm going to look at my unit circle. Find angles with a y value of negative root 3 over 2. So that occurs quadrant 3 and 4. So negative root 3 over 2 are these two. That's 4 pi over 3, 5 pi over 3. Since it doesn't ask for any other answers, and these answers fall within one revolution of the unit circle, this is it. Next example is a little weird in how you treat it. All right, so I need you to remember that what's inside these parentheses, that's called an argument. All right, so tangent of an argument equals root 3. So I'm going to solve as if I don't have a theta plus pi over 2 here. All right, I can't separate this out yet. Actually, no, I can. 100% can. Let's do inverse tangent. So inverse tangent of root 3 equals theta minus pi over 2. All right, so here's the issue with doing an inverse tangent, though. All right, inverse tangent only gives me one solution. Well, how many times on the unit circle is tangent positive? Twice. Because it's positive in quadrant 1, which is what I'm going to get originally, and quadrant 3. And since I want all solutions on 0 to 2 pi, I need both solutions. So I'm going to get the regular one. So inverse tangent of root 3, positive root 3 is pi over 3. what's the other one? Well, the quadrant 4 angle. Or excuse me, quadrant 3 angle, which is 4 pi over 3. Okay, now I can add pi over 2 to both of these. So if I add pi over 2 to pi over 3, all right, just so you can see it happen. Those have a common denominator of 6. Multiplied by 3. So when I add them together, I get 5 pi over 6. I'm going to do the same with a 4 pi. We're going to add pi over 2. Common denominator 6. Multiply by 2. So 8 pi. Multiply by 3. So that's going to get me 11 pi over 6. Recognizing the argument here is going to be key. The argument for tangent is just x. If x plus 3 was inside the argument for tangent, it would be inside both parentheses like that. It's not. So I'm going to distribute the 2. Kind of treating it just like it would do a regular algebraic equation. I'm going to subtract the tangent x. I'm going to isolate that as much as possible. Normally I wouldn't write this stuff out, but I want you to see what's happening. So when I take 2 tangent x and I subtract a tangent x, I get 1 tangent x. Subtract the 6. Okay, so I'm looking on the unit circle where tangent values are -1. This is a y over x, -1. Opposite signs occur in quadrant 2 and 4. And I'm limited on my domain. So where opposite signs occur, 2 and 4, and since I'm getting -1, the x and y need to be the same. That is 3 pi over 4 and 7 pi over 4. All right, a little harder on this one because I have mixed trig functions. I have sine and cosine. So I am going to treat it like a quadratic and get it to equal 0 by subtracting 6 sine t. And the reason I'm doing that is because I know it's going to be a common factor. It'd be a GCF. The GCF here is going to actually be 2 sine. So I'm going to have 8 cosine t minus 3. And just like a quadratic, I can set each of these factors with a 0. So divide by 2, where t equals 0 in degrees. So that'd be the y value equals 0. So that would be 0 and 180 degrees. On this 8 cosine t minus 3, we're going to add 3. We're going to divide by 8. Not a unit circle value. All right, so I'm going to take the inverse cosine in degrees. Of 3 over 8. 67.976. So I need you to remember that cosine is positive in quadrants 1 and 4. So the 67.967 or 976 is a reference angle. So what is this distance? Okay, I also need it to be that distance. So our other angle It's going to be 360 minus the 67.976. Okay, because these two are the same. And since I want this entire angle, I'll take 360 and subtract the reference. So 292.024. One thing I noticed on your midterms is that make sure you put the symbols. Degrees gets a degree symbol. Just like I just fixed that 0. Degrees get a degree symbol. On our previous example, I was able to factor out a sign. Okay, made life easy. Once I separated it out, this was one trig function here, one trig function there. I can't do that on this one. All right, because I have this minus 1. Okay, I can't, there's no GCF. I can't do it. So I want to try and make the trig functions to be the same. So I know that I can change sine squared into 1 minus cosine squared. And distribute. Combine your like terms. All right, so what I'm going to do now is I'm actually going to get this in the correct order and multiply by -1. And so what I mean by that is that this needs to be positive. And it needs to be first. So positive 2 cosine squared. So I change this sign. I'll change this sign. So a positive. We change those two. We need to change this one. So minus. And now I'm going to factor. All right, I'm going to treat it like a quadratic. We're going to change cosine squared to x. Multiply leading coefficient times the constant. Factor pairs. It's got to add to be 1. So the way that happens is if 1 is negative, break it up. Group GCF here. That's x. GCF here. There's not 1. So pull out a positive 1. Common binomial factors. And then whatever is left. Change those x's back to cosine. Set them equal to 0. Solve them. All right, yes, I'm limited 0 to 2 pi. Cosine is positive in quadrant 1 and 4. So angles with an x coordinate of 1/2 in quadrant 1, pi over 3, and in quadrant 4, 5 pi over 3. On that one, we're going to add the 1. So where cosine is a positive 1 is at 0. And that's the only one between 0 and 2 pi. 2 pi is not included because of the parentheses. All right, I'm going to show you 2 different ways of getting this. All right, this one specifically says solve this on 0 to 2 pi. So I'm going to show you all solutions, and then I'm going to show you how to get the solutions on our interval. So for all solutions, okay, we're going to solve this as if I don't have a 2x here. Okay, so that means I'm thinking what angles on my unit circle have an x of 1/2. Well, it's pi over 3. And that is 5 pi over 3. So all solutions be plus 2 pi k. But the argument is a 2x. So this is really 2x equals 2x equals. Okay, well, to get rid of that 2, I need to divide everything by 2, multiply everything by 1/2. Okay, so we distribute. Distribute there, I'm going to get pi over 6. Distribute there, I'm going to get pi k. We do the same thing on this one. Distribute. Distribute, that's 5 pi over 6. Distribute pi k. So these two give me all solutions. This is what I would do if that's what it's asking me to do. All solutions. Okay, it's not how I would solve this. Okay, so what I would do, all right, I'm going to go back to my cosine. 2x equals 1/2. Where my angle is equal, where I have my x of 1/2, we know it's pi over 3 and 5 pi over 3. But let's say I rotate around. 1 full circle from pi over 3. All right, so that would be 7 pi over 3. Because we would take pi over 3 and add 2 pi, which is the same as adding 6 pi over 3. Okay, so we'll do the same thing with 5 pi over 3, so we'll add 6 pi over 3 to that. Okay, and then we're going to rotate around from these two. So add 6 pi over 3. That is 13 pi over 3. Then add 6 pi over 3. That's 17 pi over 3. Okay, you just kind of keep going for a minute. I'm going to stop there for now. All this is 2x. Now, just like I did over here, we're going to multiply everything through by 1/2. So we distribute. Distribute, that's going to be pi over 6. 5 pi over 6. 7 pi over 6. 11 pi over 6. 13 pi over 6, and that's where I'm going to stop because I'm supposed to stay between 0 and 2 pi. 13 pi over 6 is too big. So these are my only 4 solutions. Similar process, cosecant 3x equals -2. The first thing I'm going to do is do the reciprocal. So that's sine. The argument stays the same though. And let's say I wanted all solutions. Okay, so I'd look for angles where the cosine, or excuse me, the sine is -1/2. Oh shoot, sine is negative quadrant 3 and 4. 4 pi over 3. 5 pi over 3. Okay, but this is 3x. Okay, full rotation, so plus 2 pi k. 3x. So you're going to multiply everything through by 1/3. Tell me why I said 4 pi over 3. This is going to be not 4 pi over 3. Give me my eraser. It's going to be over 6. This would be, let's see, 7 pi over 6 and 11 pi over 6. Okay, I fixed it. Distribute. Distribute. That's going to give me 7 pi over 18. Distribute here is not going to be pretty, but it's going to be your answer. It's going to be 2 pi over 3. Okay. Do the same here. Distribute. 11 pi over 18. Distribute. Those give me all solutions. It's not asking for all solutions. It's asking for the answers between 0 and 2 pi. So I'm going to go back to this. So my angles are 7 pi over 6, 11 pi over 6. Okay. Then we're going to rotate. Okay, so 7 pi over 6 plus 2 pi. Common denominator, that can make it 7 pi over 6 plus 12 pi over 6. So I'm going to add 12 pi over 6. So I add 12 pi over 6. That is 19 pi over 6. Add that. 23 pi over 6. Rotate from here. So 19 plus 12 is, oh, that's 31 pi. Add 12, that would be 35 pi. Yeah. All right, so multiply through by 1/3. It's going to give me x. I multiply 1/3 by 7 pi over 6. 1 times 7 pi, 3 times 6, so 7 pi over 18. Distribute here. So that's going to be 1 times 11 pi, 3 times 6. So 11 pi over 18. Distribute. 1 times 19 pi, 3 times 6. And the drill, keep going. 1 times 23 pi, 3 times 6. And I'm looking for 2 pi here, so that would be 36 pi over 18. I distribute there. So 31 pi over 18. Distribute that last one, be 35 pi over 18. If I go any farther than that, I'm going to be too big because 2 pi would be 36 pi over 18. That one had a lot of solutions. All right, last one. I've got 3 sine 2 beta plus 5 sine beta equals 0. We're going to use an identity here. We're going to use double angle for sine. So double angle for sine is 2 sine cosine. Original 3. Distribute. And then what I'd want to see now is if I have a GCF. And I do. Fine. I'm going to pull the sign out. Six cosine beta 5. Set each of those equal to 0. On 0 to 2 pi, the sine, the y is 0. On 0 and pi. For here, subtract the 5. Divide. We're going to take the inverse, and we need to remember that cosine is negative in quadrant 2 and 3. All right, so we're going to take inverse cosine. We're going to go back to radians. 5 over 6. 2.556. Okay, so issue here is that gives me this angle. It does not give me this one. Okay, so we need to find a reference angle here. So we're going to do pi minus 2.556. So 0.586. So that gives me my pink angle here. Gives me all of this. Well, that's the same over here. All right, so now I'm going to take that pi and I'm going to add the reference angle because I am in quadrant 3. So we're going to take pi and add that reference angle. 3.727. All right, so all those things that we learned in Unit 1 with reference angles, or Unit 5, excuse me, with reference angles, those still exist. All right, so if you're thinking about what you're going to put on your note sheet for your final exam, reference angles would be something I put down. All right, and that takes us to the end of solving.